39,000 feet above the North Atlantic, the air outside the cabin window is cold enough to freeze human skin in seconds. The temperature gauge, if you could mount one on the wing, would read -57 degrees Celsius. Cold enough that exposed metal becomes brittle. Cold enough that moisture in the air crystallizes instantly into ice. And strapped beneath that wing, spinning at 14,000 revolutions per minute, drinking in that frozen air by the ton every second, is a machine built from aluminum alloys and titanium composites that should, by all common sense, be frosting over and seizing up within minutes. The fan blades alone move enough air every second to empty a suburban living room. The inlet cowl, that smooth circular mouth at the front of the engine, is a scoop designed to grab the coldest air on Earth and funnel it into the heart of a device that depends on continuous, uninterrupted flow. And yet the engine runs. Smooth. Hot. Flawless. Here is the question. At cruise altitude, where the outside air temperature sits at -57 Celsius, why does a jet engine not freeze solid? Why do ice crystals not choke the inlet, clog the compressor blades, and send the turbine into a catastrophic stall? The answer is not insulation. It is not electric heating elements bolted onto every surface. The answer is that the engine solves the problem of cold by weaponizing its own heat, by stealing energy from the very process that makes it work, and by turning the physics of compression into a furnace that keeps the ice at bay. By the end of this, you will understand the trick, and you will see why the coldest place a jet ever flies is also the place where parts of that engine glow cherry red. Start with the air itself. At 39,000 feet, the atmosphere is not just cold. It is thin. The air pressure up there is roughly a quarter of what it is at sea level. Oxygen molecules are spread out, sparse, moving slowly in the frozen stillness. A human lung cannot extract enough of it to stay conscious. But a jet engine is not a lung. It is a compressor wrapped around a combustion chamber, and its entire job is to take that thin, cold, useless air and squeeze it until it becomes dense and hot enough to burn fuel efficiently. The engine does not passively accept the air. It forces it inward, crushes it, heats it, and ignites it. And that heating begins the instant the air crosses the inlet threshold. Here is the mechanism. When you compress a gas, you do work on it. You shove the molecules closer together. They collide more often, move faster, and the temperature rises. This is not a side effect. It is the ideal gas law in action. Pressure, volume, and temperature are locked together. Squeeze the volume down, and if you do it fast enough, the temperature climbs. A bicycle pump gets warm in your hand for exactly this reason. The air inside is being crushed into a smaller space, and that compression energy becomes heat. Now scale that bicycle pump up to a machine with a fan diameter of nearly 3 meters, spinning at 14,000 RPM, forcing tens of thousands of kilograms of air per hour through a series of rotating and stationary blades designed to compress that air by a ratio of roughly 30:1. The cold air outside enters at -57 Celsius. By the time it reaches the end of the high-pressure compressor section, before a single drop of fuel has been added, that air has been heated by compression alone to somewhere between 300 and 400 degrees Celsius. The engine has turned a freezer into a furnace using nothing but mechanical energy and physics. Let that sink in. The air that was cold enough to kill you 10 seconds ago is now hotter than a kitchen oven, and it has not even reached the combustion chamber yet. When fuel is injected and ignited in the combustor cans, the temperature spikes to between 1,500 and 2,000 degrees Celsius. The turbine blades downstream, forged from nickel-based superalloys and cooled by precisely drilled internal air passages, operate in an environment that would melt ordinary steel in seconds. So the engine is not cold. The engine is a controlled inferno. The question is not how to keep it warm. The question is how to keep the parts that must stay cold from being destroyed by all that heat, and how to steal just enough of that heat to prevent ice from forming where it matters. This is where bleed air enters the story. Bleed air is exactly what it sounds like. Compressed air is bled off, tapped from the high-pressure compressor stages before it reaches the combustion chamber. This air is still scorching hot from compression, typically between 200 and 300 degrees Celsius, and it is still under high pressure. Engineers route this bleed air through a network of internal pipes and ducts to the places where ice is most likely to form. The engine inlet cowl, the leading edges of the wings, the slats, and sometimes the engine nose cone. These are the surfaces that face directly into the oncoming frozen airstream at 500 knots. These are the places where supercooled water droplets, still liquid despite being below 0 Celsius, will strike and freeze on contact, building up layers of ice that can disrupt airflow, add weight, and in the worst cases, break off in chunks and get ingested by the engine. Bleed air is piped into hollow passages inside the inlet lip, that smooth leading edge of the cowl. The hot air circulates, warming the metal skin from the inside, keeping the surface temperature just high enough that ice cannot adhere. The same principle applies to the wing leading edges. Piccolo tubes, narrow pipes with tiny holes drilled along their length, spray hot bleed air across the inner surface of the wing skin. The metal stays warm. The ice stays away. The system is entirely passive in the sense that it requires no electric power, no heating elements, no computers. It is thermodynamics doing exactly what thermodynamics does. Hot air moves to cold surfaces, transfers its energy, and prevents freezing. The engine is heating itself, and in doing so, it is heating the aircraft. Consider the Pratt & Whitney JT9D, the engine that powered the Boeing 747 for decades. At cruise, each engine produced roughly 50,000 pounds of thrust and consumed about 3,000 kilograms of fuel per hour. A portion of the air compressed by its 9-stage high-pressure compressor was bled off for anti-icing and for pressurizing the cabin. Engineers estimate that roughly 1 to 2% of the engine's total airflow was dedicated to bleed air systems. That seems like a small number until you calculate the mass. At cruise, a single JT9D moved roughly 250 kilograms of air through the engine every second. 1% of that is 2.5 kilograms per second of hot, high-pressure air available for anti-icing. That is more than enough to keep the inlet and wing surfaces above freezing, continuously, for hours. Now here is the part most people get wrong. The common belief is that jet engines are protected from cold by some kind of external heating system, by electric blankets or chemical coatings, or perhaps just by the fact that they are made of special metals that do not freeze. None of that is true. The engine stays warm because it creates its own heat, and it creates that heat by doing the very thing it was designed to do, compress air. The cold is not the enemy. The cold is irrelevant. The engine does not care that the outside air is minus 57 degrees, because by the time that air has traveled 30 centimeters into the inlet and started being worked on by the fan and compressor blades, it is already warming up. By the time it reaches the high-pressure stages, it is hotter than boiling water. The frost on the outside of the cowl, the ice you sometimes see clinging to the nacelle on the ground, melts away the instant the engine spools up to taxi power. The machine is self-heating by design. There is one more piece to this. Ice is not just a problem on the surfaces you can see. Ice can form inside the engine if conditions are exactly wrong. Supercooled large droplets, the kind you encounter in certain types of clouds, can survive past the inlet and make it into the compressor stages. If the air is still cold enough and the droplets are large enough, they can freeze onto the compressor blades themselves or onto the internal struts and vanes. This is called core icing, and it is rare but dangerous. A buildup of ice on the compressor blades changes their aerodynamic shape, disrupts the smooth flow of air, and can cause a compressor stall. The engine coughs, loses power, and in extreme cases, shuts down. This happened to a pair of Boeing 737 aircraft in the early 2000s, and the result was a multi-year investigation and a redesign of engine control software to recognize the condition and increase engine power automatically to melt the ice before it caused a stall. The fix was not to add more heating. The fix was to trust the heat that was already there and to manage the engine in a way that kept the core hot enough, continuously, that ice could not accumulate. Modern full-authority digital engine control systems, the computers that manage fuel flow and fan speed, now include logic specifically designed to detect the telltale signs of ice ingestion and to spool the engine up just enough to burn it away. The engine, once again, solves its own problem. Which of these machines would you least want to be standing next to at full power? A turbofan at takeoff thrust, a steam catapult on a carrier deck, or a tunnel-boring machine chewing through granite? Tell me below. Here is the synthesis, the trick you can explain to someone over coffee. A jet engine does not freeze at altitude because the act of compressing air generates hundreds of degrees of heat before combustion even begins. That heat is then stolen, bled off as pressurized air, and routed to the exact places where ice wants to form. The engine is not protected from the cold. The engine ignores the cold by being vastly, overwhelmingly hotter. The coldest air on Earth enters the inlet and within a fraction of a second is transformed into a stream of gas hot enough to glow. Everything else, the anti-icing, the cabin pressurization, the environmental control, is a byproduct of that core fact. Compression makes heat. Heat solves cold. The system is closed, elegant, and requires nothing from the outside world except more cold air to compress. Walk past a jet on the ramp in winter and you might see white trails of condensation streaming off the wing roots and nacelles as the engine runs. That is not exhaust. That is bleed air, venting overboard after doing its job, cooling rapidly in the frozen air and condensing into visible mist. It is the ghost of the heat that keeps the machine alive. It is a reminder that the engine is not a static object. It is a continuous controlled explosion, a river of fire wrapped in metal, running hot in the coldest corner of the sky. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart.